Everybody to the Algebra and Number Theory seminar. Today we're going to have a talk by Neelam Saikia from the University of Virginia. She will give us a talk on Frobenius trace distributions for Gaussian hypergeometric functions. Okay, let's welcome her.
Yeah. Thank you everyone for this nice introduction and giving me this opportunity to produce my work here. So today I'll be talking about Frobenius trace distributions for Gaussian hypergeometric functions. And this is a joint work with Cohan and Hassan Saad. So to motivate our talk, so we first consider one example. So if E is an elliptic curve, which is given by this equation y square minus y equal to x cubed minus x squared, then for each prime P of good reduction, we define these numbers AP as P plus 1 minus number of points on this elliptic curve modulo P. Then it is easy to see that these numbers are integers and they are bounded integers. And in fact, there is a very well-known bound by Hassa, which gives that these numbers AP are lying in this interval negative 2 square root of P to 2 square root of P. So now if we consider these numbers like A of P over 2 square root of P, then these numbers are real numbers which lying in the interval negative 1 to 1. So now if we collect these numbers AP by 2 square root of P for prime up to 10 to the 9, then and if you make this histogram of these values, where on the x-axis we divide this in subintervals, and on the y-axis we take the frequencies. So this histogram looks like a square semicircle. And this picture clarifies one of the most famous conjecture in number theory. It's called Satotate conjecture. So let me just give you briefly what the conjecture is. So if E is an elliptic curve which is defined over the field of rational numbers without complex multiplication, then for each prime P of good reduction, we can define this angles theta P, which is associated with the traces of Frobenius of the elliptic curve E in this way. Since by the Hassa bound, we can always get an angle theta P which satisfies this equation. Then these theta P's are lying in this interval 0 to pi. Then for any two real numbers alpha and beta, if we take this ratios of this term, where we take the ratios of the primes up to x and the primes up to x, such that these theta p's are lying in this interval alpha to beta. And when we take this sequence, and when we take x goes to infinity, this sequence will converge to this definite integral of sine square theta d theta. And this conjecture was known as Satotate conjecture. This conjecture was open for a longer period of time. Recently, this conjecture was proved by Taylor and his collaborators in 2008. And this conjecture is quite deep, and it is hard to prove. But so after the Satotate conjecture was proved, there are many other directions where people find the distributions of varieties, or in fact elliptic curves over totally real number fields. They studied in those directions. But in our work, we consider these three questions. So we are looking for analogous distributions for families of other varieties over finite field. And in fact, we would be happy if we get some different distributions rather than Satotate, or maybe rather than semicircular. We'd be quite happy if we get different kind of distributions in our work. And then, of course, we know that we have to approach different framework for our distributions. So here we are looking for some structural framework that will describe other distributions. So in our work, we consider two families of varieties, so which are associated with hypergeometric functions. So before going to our main results, I'll quickly describe what is classical hypergeometric functions. So if alphas and betas are some complex numbers, then in these parameters, alphas and betas, this classical hypergeometric function is defined in this formal power series, where these coefficients, where the coefficients are some ratios of these terms, where these terms are defined as. So if k equal to 0, then it will be it takes value 1, and if k is greater than equal to 1, then it is the product of these numbers. And this kind of functions are well known, and these functions were studied since Gauss, Euler, Ramanujan. These functions has been extensively studied in literature, and by ratio test we can say that this series converges for modulus of x less than 1, which defines an analytic function in the complex numbers. So this is a classical hypergeometric function. Now we'll see some of their connections with elliptic curve. Okay, so if we consider an elliptic curve over the field of complex numbers, then we know that over the field of complex numbers, this elliptic curve is a one-dimensional torus. So if you wish to determine the torus, we need to get a lattice. So that means we need two generators of the lattice. So if you want to calculate the generators of the lattice, which is associated with this elliptic curve, then it turns out that the generators of this lattice are given by the elliptic integrals. In fact, this was proved by Gauss. He considered the Legendre form of elliptic curve, which is given by this equation, where this equation varies with respect to lambda. So he proved that if lambda is a real number which is lying between 0 to 1, then he proved that this the period, which is the generators of the lattice, which is called the period of the elliptic curve, which is associated by this 2f1 hypergeometric function in this way. So this was proved by Gauss. So this kind of results are not very common. So recently, McCarthy considered the Gaussian form of elliptic curves, which is defined in this way. This function also depend on lambda. That means if lambda varies, this function varies. Then he proved that if lambda is a real number, then the period of the real period of this Gaussian form of elliptic curve is associated with this 3f2 functions in this way. In fact, he proved that this 3f2 functions is connected with the square of the period. It's not like the period is related to this 3f2 function. The square of the period is related to this 3f2 hypergeometric functions. So now, since we have results that are associated with the classical hypergeometric function and elliptic curves over C, so we can consider their finite field analogues. So in our work, we would like to study these two families of elliptic curves over finite field. So since classical hypergeometric functions are related to the period of these two families, we could ask what about their finite field analogues. So here comes the function which given by Green. So Green developed hypergeometric function over finite field, which is considered as the finite field analog of classical hypergeometric function. So he considered this function where he used the parameters as the multiplicative characters. So in the classical hypergeometric functions, we have the parameters are complex numbers, but in Green's function over the finite field, the parameters are multiplicative characters of finite field. So what is the multiplicative character of a finite field? So it is a homomorphism from the group of non-zero points of the finite field FQ to the non-zero points of the complex numbers. So he replaced the complex numbers as these parameters, which are the multiplicative characters. and he defined this function as this character sum, where the sum runs over all the multiplicative characters of the finite field FQ, and where these symbols, so this looks like the binomial, and which is known as the binomial, so which defined as this normalized Jacobi sums. So here we use this notation as Q. So that means when we talk about finite field hypergeometric function, we always use the suffix Q here. And Green also developed some of these some of the properties of this hypergeometric functions, which are analogous to classical hypergeometric functions. That's why this function is known as the finite field analog of hypergeometric functions. So so today we are not talking about much of the properties or in or detail how this Green developed these functions. So if you want to see how these functions he developed, you may go through his paper, which is in Transactions of AMS, for where he gives a beautiful theory where how he developed these functions. So in today's talk, we now pick some notations because you know these functions are very looks I mean it's big, so that's why we fix some notations so that we have, I mean, because of lack of space, we fix some notation. So here phi, so it denotes a quadratic character, that is a character of order 2. And we always represent the trivial character by this symbol epsilon. So one of the simplest hypergeometric functions, simplest in some way, we can say that this function is the simplest function because it involves only trivial and the quadratic characters. So if we have this hypergeometric function with n quadratic characters and n minus 1 trivial characters, then we use this notation nfn minus 1 lambda to denote this function. Okay, so now this is an mantra. It's called arithmetic and geometric Manta. So that means so whenever we have the real period that gives given by this classical hypergeometric function, so we could ask what is their final field analog. That is, if we replace this numbers 1/2 and 1 in the finite field setting, if we replace these numbers by this quadratic and trivial characters, then what could be their finite field analog, like like that is that are associated with the elliptic curves. So here this is one of the oldest theorem of Ken Ono. So what he proved that if we consider the traces of Frobenius of an elliptic curve, then for characteristic of the finite field which is greater than or equal to 5, then for those hypergeometric functions over finite fields, so this 2f1 function is associated with the traces of Frobenius of this legendary form of elliptic curve. And in fact, again, analogously, for the Gaussian family of elliptic curve, the square of the trace of Frobenius is naively associated with this 3f2 function in this way. So these are the finite field analogs of these hypergeometric functions. So in our work, what we are looking for, so we would like to study these two functions, 2f1 and 3f1 functions, and we would like to study the distributions. So the first question that I would like to study is, we would like to study the limiting distributions for these 2f1 functions. So now to fix the range of this function, we consider the renormalized values of this function so that they lie in a fixed interval, which is -2 to 2. So we would like to study what could be their limiting distribution. So this is our first theorem. So we prove that for any real numbers a and b, which is lying in this interval -2 to 2, then a limiting distribution of the renormalized values of this function such that the renormalized value lying in this interval a b. So this limiting distribution is converges to the definite integral of this this integral, where this looks like.
Neelam, I have a quick question. Why is this interval? Is it specific? Like, what's the importance of this interval?
From -2 to 2. Did you mean this interval, -2 to
Yes,
2?
yes, yes.
Yeah. So here, because we want to fix the values so that it will lie in an interval. Since you know the connection between this 2f1 function with the traces of Frobenius of this elliptic curve a lambda, and since by Hasse bound we know that this this value is like 2 square root of p minus 2 square root of p to 2 square root of p. So using this relation, we can bound this 2f1 in this interval -2 to 2.
Okay. Thanks.
So yes, so for this 2f1 function, the limiting distribution is semicircular, which is like the Satotate distribution. And now we'll see we'll see the histogram for the 2f1 function. So if we consider this histogram for the prime p equal to 93,283, if we consider this histogram where on the x-axis we divide this in the subintervals, and on the y-axis we take the frequencies. So it looks like this. And then so if we take p goes to infinity, so we'll obtain that this histogram is converged to this semicircle. Okay. So from our theorem, we obtain that the legendary form of elliptic curves over large finite fields, so they behave like original Satotate conjecture. So the second question we would like to study is the same. Like what could be the limiting distribution for this 3f2 hypergeometric function? And also here we also renormalize these values of this function so that they lie in this interval -3 to 3. So in our theorem, so we prove that if a and b are two real numbers that lie in this interval -3 to 3, then the limiting distribution of this renormalized values of 3f2 functions that live in this interval a to b is converged to this definite integral of f of t, where f of t is this particular function. Okay. And we call this distribution as Batman distribution. So why we call this as Batman distribution? So it will clarify from our next slide. So if we consider this histogram of the 3f2 values, then this histogram looks like Batman. So that's why we call the distribution is the Batman distribution. Okay.
So now, Neelam, I have one small question. Yeah. So maybe this is a stupid question. Why you take this prime? The prime matters, so you can take any prime and get a distribution like this.
We consider so it less than 10 to the 5. I mean, because other than so we are in my computer actually because these are done like in my computer. If I do a large prime, it will take lots of time. So this is the largest prime that we could get a picture. I mean, that's right. So yeah, so now the problem is how do we obtain the distributions? So here we adopt the method of moments. So what we do, so we'll compute the power moments for this 2f1 function as well as for 3f2 functions. We compute the power moments, and then we will try to obtain their asymptotic as q goes to infinity. And once we have the asymptotic for the moments, then we'll obtain the moments for the random variable of the expected distribution, and then we compare this their moments and we get the distribution. So while calculating the moments for these two 2f1 and the 3f2 functions, we end up having the moments in terms of weighted sums of class numbers. So let me just remind you quickly what is a class number. So if -d is a discriminant, then h of -d, it is the class number of the quadratic order of discriminant -d. Then its Hurwitz class numbers are of two types. So here h of d, so this capital H of d, so this is the sum of all the class numbers. This is where the sum runs over all the orders lying between O and the maximum of O. So maximum O means the ring of integers of the complex number field, and h star of d, so this is the weighted sum of these class numbers. where omega, where the weight is given as the half of the number of roots of the unity in O prime. In fact, h of d and h star of d, these two are same unless the roots of unit, unless the order, maximal order is the Gaussian integers and the cube root of -1. So, and if the maximal orders are different from these two particular orders, then we always have h of d is h star of d. So now we'll see how the 2f1 moments look like. So in this theorem, we obtain the 2f1 moments for this function. So which is equal to the sum of this weighted sums of this class numbers, where the sum runs over all the s that lying in this interval -2 square root of q to 2 square root of q, such that the s is co-prime to p. So, and s satisfied this congruence condition. We'll see later that this congruence condition is totally group theoretic. Again, the even moments for this 2f1 function, we will obtain a similar kind of formula. Apart from this extra constant that appears here, where this extra constant sp. So this is the degree of a characteristic P supersingular locus, that is the number of isomorphism classes of supersingular elliptic curves over fp bar, and which is approximately equal to P over 12. And this and another constant CQ. So this is a rational constant that lying in this interval 0 to 6, and it could be understood as the average of the number of average of legendary form of elliptic curves that lying in isomorphism FQ isomorphism class, whose stress is up to is equal to 2 square root of Q or 2 square root of -2 square root of Q. So now we'll consider the odd moments. So if Q congruent to 1 mod 4, the odd moments for this 2f1 function, we have an analogous formula involving this kind of class numbers. And if Q congruent to 3 mod 4, in this case we are lucky. We have the odd moments are end up being equal to 1. Here there is no class number. Okay. So now now we'll give a brief sketch of how we get these moments. So now first of all, consider this number, which is represented by this notation IGSQ. So this represents the number of isomorphism class of elliptic curves, which stress is given by this, and which contains this group G. So this represents the number of isomorphism classes with this prescribed group G and with fixed stress S. And so now we want to know what is this number. So now for in particular, if G equal to Zn times Zn, then all the numbers are given by Scoof. So what he proved that if S is co-prime to P, and if n square divide Q plus 1 minus S, and n divides Q minus 1, then this number is given by this Hurwitz class number. So this is an important theorem which plays an important role in our work. So now we'll give how this the 2f1 moments are coming. So here, since we know that the 2f1 function is associated with the traces of Frobenius of legendary normal form of elliptic curves, so everything now become in terms of calculating the moments for the traces of Frobenius of this legendary form of elliptic curves. So that's why what we do, we organize the legendary form of elliptic curves in their FQ isomorphism classes. So here, to do this, we use two facts. So one important fact is that we know that the legendary normal form of elliptic curves contains this subgroup C2 times C2. And when the J invariant of the curve is different from 0 and 1728, then this set map to the same J invariant. That means if we consider an legendary normal curve where the lambda is one of these values, then they are either isomorphic to over FQ, or they are quadratic twist of each other. So using these facts, we organize the legendary form of elliptic curves in their FQ isomorphism classes. And once we organize them in their classes, we apply Scoop's theorem, which gives the connection to the class numbers. So this is how the 2F1 moments we have derived. And now for the 3F2 moments, we did similar kind of calculations. However, these calculations are slightly different, because as you know that the 3F2 function is associated with the square of the trace of Frobenius of this Gaussian form of elliptic curve in this way. Therefore, now to obtain the moments formula for this 3F2 function, so we have to obtain the even moments for this for this traces of Frobenius for this Gaussian form of elliptic curves. So here again we count the isomorphism classes of Gaussian form of elliptic curves, and once we organize their isomorphism classes, we apply Scoop's theorem. So for this we obtain an theorem. So here what we do, so we consider all the values of lambda for which the Gaussian form of elliptic curve has trace either trace is equal to s or trace equal to minus s. Since we are here, we considering the even powers, so it doesn't matter whether we took s or minus s. So here we consider all those lambdas for which the trace is equal to s or minus s, and we count those lambdas, and we obtain that this sum is equal to the s to the 2m times the sizes of these two sets. For the first set ISQ, so this is the set of FQ isomorphism class of elliptic curves whose trace is either s or minus s. And I2SQ, so this is the class of so it is a subset of ISQ, where the two torsion points are given by this group. So using these two sets, we organize this sum where and represent that this sum is equal to the cardinality of these two sets. Similarly, if we consider this weighted sum here, again here we consider the same sum where this lambda varies over all where this the trace is equal to either s or minus s. So and we have given a weight here. So if we consider this sum, we obtain that this sum is equal to the cardinality of these two sets. So this using this theorem, we obtain our 3F2 moments, which eventually gives in terms of the some weighted sums of class numbers. So these are in this way we obtain the 2F1 moments and 3F2 moments in terms of weighted sums of class numbers. So now once we have the moments in terms of class numbers, now our next goal is to obtain their asymptotic formulas. So to obtain asymptotic formulas, so what we will do, so we'll extensively use Jaguars function. So here's so this is the Jaguars function, where this function has two parts. So this is the generating function of the class numbers, and where this is the definite this is called the this is the indefinite gamma integral. So this way so this is the Jaguars function, which is a harmonic mass form of weight 3/2. So this function we use repeatedly to obtain the asymptotic formulas for our power moments. So to motivate how do we obtain our asymptotic formulas, we first recall one of the famous theorem of Eclair. So what Eclair proved that, so he considered this sum of these class numbers, and we obtained that this sum is equal to is equal to sum of these two divisor sums. where sigma 1 of n is the usual divisor sum of n, and lambda 1 n. So this is the sum of the divisors of n which are less than n by 2. So Euclid proved that this sum is equal to these two divisor sums. So from here we can see clearly that if we have such kind of formulas, we easily obtain asymptotic formulas. So in fact, in our work we would like to estimate this kind of sums of class numbers. So here, if you can notice, so if you put m equal to 0 here, so this sum is exactly look like what Euclid's did. So here, as you can see here, s is an even integer. So we can write s by s over 2 so that this 4 get cancelled and we get a similar kind of sum like here for m equal to 0. So for m equal to 0, our asymptotic follows easily from this Euclid's formula. So now our job is to obtain the asymptotic formulas for m greater than or equal to 1. So this is our next aim. So to do this, we use a method which I'll explain you in a bit. So first, let me just give you remind you what is a Cohan ranking bracket operator. So Cohan ranking bracket operator is an operator that can be applied for two smooth functions. If f and g are two smooth functions, or maybe we can say that they are non-holomorphic modular forms of weight k and l, then the muet Cohan ranking bracket operator is which is applied for these two functions f and g. So this is defined as this sum of this combinatorial sum of this sum in the derivatives of f and g. And one of the important fact for this operator is that this preserves modularity. So if f is a modular form of weight k and g is a modular form of weight l, then this operator will produce a modular form of weight k plus l plus 2 mu on the same congruent subgroup. So to obtain our asymptotic formulas, we use this operator for two seats of modular forms. So this is I briefly give you the structure, how we obtain the asymptotics. I apologize because I won't be give you a full, the detailed calculation for this asymptotic formulas. I'll just give you the main tools that we are using. So if so here, as we have this Jaguars function, which is h of tau, and we use these two theta functions, and then we apply the Cohan ranking bracket operators for these two pairs of for two functions separately. And when we apply the Cohan ranking bracket for these two pairs of functions, we obtain non-holomorphic modular forms, where the coefficients of those modular forms are some weighted class number formulas. And after treating those coefficients carefully, we obtain the formulas that we need to estimate. And then what we do, once we have the coefficients of this modular forms as the sum we need, we for the even moments case, we apply the Cohan's conjecture. So this conjecture was proved by Martins in his thesis. This conjecture is all about saying which produce sequences of modular forms. So once we have this theorem, we can say that the coefficients that are modular form. And then for the odd moments part, we basically use that once we apply this Cohan ranking bracket operators, so which gives non-holomorphic modular forms. So then we apply holomorphic projection on this bracket operators to produce them as modular forms. Then, so once we have modular forms on the right side, we can estimate the coefficients by Delign's theorem. So that's how we estimate our moments as q goes to infinity. So after calculation or about 20 pages, we obtain that for the 2f1 functions, the even moments for this 2f1 function goes to 0 as p odd moments for this 2f1 function goes to 0 as p goes to infinity. And for the even moments for this function goes to this Catalan number to 2n over n 2n factorial over n factorial into n plus 1 factorial. So from here you can imagine, like, so yeah, so this time we have the Satotate because the moments are same as for the Satotate distribution. Then for the 3f2 functions, we obtain that the odd moments are again converse to 0, and for the even moments we obtain that this this converts to the sum of this weighted sum of this Catalan numbers. So from here you can see that this will represent some kind of truncated hypergeometric functions. So yeah, so now we have the asymptotic formulas for the moments for the 2f1 as well as for 3f2 functions. So now, what could be the criteria for the distributions? Like we have the moments, now how we obtain the distributions. So this is a general question in probability. So if we have a sequence of, or maybe a family of bounded functions, and if we know their moments, how we obtain their distributions. So here we apply the method of moments. So to obtain our distribution, we prove two lemmas separately. So what we prove, if we have a family of functions f of p where the moments are given by these two terms, then the limiting distribution for this family of function is converged to this definite integral of the circle. So, and in the second lemma, we'll prove that if we have the limiting, if we have the moments for these functions are 0 if m is odd, and if the even moments are given by this sum, then the distribution would be given by limiting distribution would be given by this integral of f of t. So since this for the 2f1 function, it looks like the Satotate. So here I'll give you how this lemma how this lemma goes for the 3f2 functions. So this is the sketch of the proof. So here we consider this probability space that contains this interval -1 to 1 and this curl f. So this is the Lebesgue measurable subsets of this -1 to 1, and mu bat. So this is the major, which is the integral of this f a to b f of t dt, where f t is our earlier, which is like this. F of t is given by this. So then what we do here, we consider this random variable x from -1 to 1. So which is defined by x of t equal to t. So when we compute the moments for this random variable, so the moments would be like the integral of a to b, and then f of t into t to the m dt. So that means it will be an integral. So here we so once we have the integral of f of t dt, once we put the values of ft and we apply some kind of transformation in the integral, we'll see that this integral will look like this. And from the theory of Apple hypergeometric function, we know that this integral is given by this Apple hypergeometric function in this way. And from and we know that this f1 function can be written as the product of two f1 hypergeometric functions, where one of the function can be evaluated by applying Gauss theorem, where we know the Gauss evaluated the function, or the 2f1 function value at 1 can be obtained from Gauss theorem, and the other part of the hypergeometric function, so it will give this this function which is appearing here. So this is the way we obtain the moments for this expected for this random variable. And yeah, so now we have the moments for this random variable. So now what we'll do here, so we consider the probability space here, and we consider the random variable xp as f of p. So then, since the f of p has the same moments as the random variable x, so then, and the moments, they form a positive, so the moment generating function has positive radius of convergence, therefore the limiting distributions are same. So from here we can say that the distribution for the 3f2 function is given by f of t, integral of f of t. So yes, this is these two are our main theorem. For the 2f1 function, we obtained that the limiting distribution is semicircular, and for the 3f2 functions, we obtained that the distribution for the 3f2 function is the Bachmann distribution. So yeah, so here these are the histograms that we have shown earlier. Yeah, that's it.
Is that you're finished?
Yes, yeah.
Okay, well, first of all, are there any questions? Does anybody have any questions?
Well, I think it's a very nice result. So let me just naively asking that the Satotate there are different Satotates, one versions for one fixed modular form. You look at the AP, you can talk about Satotate. Mm-hmm. Now you are taking an average of the fiber.
Yes.
So you're getting this semicircular picture.
Mm-hmm. Mm-hmm.
And the picture on the right-hand side is actually relating to another object. Basically, the 3f2 is relating to another 2f1 by the symmetric square. So it's actually as what you have in introduction. It's the symmetric square of 2f1, 1/4. You can use 1/4 or 3/4 on the top and 1 down there. Mm-hmm. So my question is, if I know an object, which is basically just like your 2f1, right? If I'm going to extract all the information, forgetting about the class number. So if I have another family, say if I replace the parameters, 1/2 by something slightly more general, and if I know, say fiber-wise, I know for the non-CN case, there is a Satotate fiber-wise. Do you expect to get a picture like the semicircular picture on the left?
So you mean if we have, suppose if we have a Satotate for one function, so you want, okay, can we have so if we consider the symmetric powers and of those function, so can we have the Satotate?
So say if I change your 2f1 into 1/3, 2/3 on the top, right? So it's somehow like the cubic case.
So it looks like somehow so here so in all our theorems we explicitly calculate the traces of Frobenius. So which is from where we can, so if it is so like if the hypergeometric function is related to, I mean, up to some constant, if it is related to the traces of Frobenius of an elliptic curve, then you can expect that for that function we could have the Satotate distribution. But if that function is not directly related to the traces of Frobenius of the elliptic curve, for example, from here you can see like the for the 3f2 functions we have that the 3f2 function is related to the square of the trace and with some extra terms. So here we have different kind of distribution. In fact, we have did some kind of calculations for other hypergeometric functions like 4f3 and then 5f3, which involves parameters as phi and trivial characters. There we won't get Satotate distribution. I mean, the distribution is not semicircular. I mean, it's kind of, it's a mystery, because as you know, like 3f2 function, we can write it as sum of the 2f1 function with some weight, right? Like, so Green has a result that express that if we have an n-1 function, that we can represent that function as sum of as a weighted sum of a lower order hypergeometric function, right? So here so from here you can see that this 3f2 function, we can write it as some weighted sum of 2f1 functions, and here we have a totally different distribution. So my guess is if we can somehow relate those functions directly up to some constant, if we can relate to some normalized values of the traces of Frobenius of an elliptic curve, then we might expect Satotate distribution. I think apart from that, I'm not sure. Like, how do we?
Okay, yeah, because your two peak, the Headman's two peaks, it's causing by when you take the symmetric square, you do see p and minus p quite a lot. After normalization, they're giving you 1 and -1.
Do we have another question?
You mentioned that you already got some interesting distributions for other cases. Like what's the shape look like? Do you get like similar shape as Batman? Or?
No, I'm saying for the 4f3 functions, we obtain that we want to make make a histogram which doesn't look like Batman or this semicircular, which are, I mean, totally different. But so from the histogram we could guess, okay, we'll obtain different distribution, but how to prove those distributions, we haven't done any kind of.
So does it more or less like a ball, but it's a different shape, or it going up and down?
So for 4f3 function, it will looks like a pyramid. When we construct the histogram, it looks like a pyramid. And for the 5f3, 5f4 functions, it's look like this, like it will go like this, and I think we could get some kind of singularity on the top, on the y-axis. It looks like that. I mean, yeah. So the histograms looks like that, but apart from that, we haven't, because here we have a nice connection with the elliptic curves for 2f1 function and 3f2 functions, but for 4f3 and 5f4 functions, we have no such kind of results. So that's why it comes like we have to calculate classically, like we have to estimate the character sums. So that's the main difficulties.
Nice control of the moments of the character sums.
Is there
And
another
your
question?
paper is already posted at archive?
Which one?
This paper you're talking about, are they already published?
Yeah. This paper is an archive. Yeah, it's an archive.
Yeah, again, I think it's a nice result.
Do we have another question? Well, just one comment about all these shapes. What you see as the semicircular distribution can be interpreted conceptually as the Haar measure for GL2, or rather for the unitary group U2.
Yes.
Now, when you have other families of varieties, what we call the motivic Galois group won't be GL2 anymore. So for CM, the motivic Galois group is GL1. That's where you get a flat distribution. For GL2, you get the unitary group. Now, if you go to higher genus curves, and I was going to suggest one thing you might look at is to get away from elliptic curves, is try to go to genus 2, for example. You'll start to see the shapes coming from the Haar measure for SP4, or rather I should say, the unitary form of SP4. Now, I actually did experiments myself with this with the REU students 20 years ago. And we looked at genus 2 curves. We looked at the Satotate distributions for genus 2 curves. And we got all kinds of interesting shapes, but they were exactly the ones predicted. You can actually find these predictions. I mean, the Haar measures are written down explicitly in this book by Katz and Sarnak. For example, now the semicircular shape is what you get for an elliptic curve because the motivic Galois group there is GL2. That's the conceptual explanation. Now, I'm not sure about the 3F2. I think as Ling says, I think you're taking symmetric powers or something.
In fact, I think for 3F2 functions, so here comes the orthogonal groups with orthogonal matrices with the Haar measure. It's the distribution is same for the orthogonal O3.
Right. So I think the answer to this question of what shapes you expect, you should first decide what shapes you should find, and then go look for them.
And backward direction.
You know, I mean, you could. But I can tell you that one interesting place to look is to start to look for genus 2 curves rather than genus 1 curves. Now, there are many of them that are related to character sums too. That's just a suggestion.
Yeah, nice. I'll look into it.
Well, anyway, very nice talk. Let's thank our speaker.